Help in Pharmaceuticals in association with Higher Secondary Principals Forum.
Hello everybody and welcome to yet another lecture in chemistry in this Prudent Scholars series. My name is Mrs. Priyanka Sawant, teacher grade 1 at Saraswat Vidyalayas, Purushottam Valavalkar Higher Secondary School, Mapsa. Students, in this unfortunate pandemic that we are all going through currently, there is so much being heard about and there's so much been spoken, a lot of hype about immunity, isn't it? There's so much being said about having your immune system strong and keeping your body strong, being able to fight any foreign infection. Now, these things were always important, isn't it? It's just that the current scenario is a constant reminder that it is important to pay attention to your health. And if you've tried to find out, you must have definitely known that one of the ways in which you can keep your body strong is by putting in the right amount and the right kind of food. That is to have a healthy diet. Now, very often when we do this topic in school, I ask my students, what according to you is a healthy diet? And impulsively they come forward and very actively they will come and tell me, in fact any one of you will tell me that a healthy diet is the one in which you take what your body requires in an adequate amount. And what is that? All the nutrients that your body needs, like the carbohydrates, the proteins, fats, the lipids, the vitamins, the minerals, all that your body requires to be taken in an adequate amount. Very true, and that's absolutely correct. But at the same time, not just that your body has to take in all this, if you pay careful attention from head to toe, you are actually made up of all these molecules, which are called collectively as the biomolecules. Your body, right from the hair has proteins, the nails, the blood is hemoglobin. Your blood constantly needs a supply of glucose, which is carbohydrates and whatnot. So all of these are, they are very beautifully composed in not just the human body, but any living organism, may it be the plants, may it be the animals, may it be the microorganisms like the bacteria, the fungi, are made up of all these molecules, and therefore they are called as the biomolecules, which is our topic of discussion today. So without wasting any time, let's go on further. So like I just said, a biomolecule is the molecule which occurs in the living organism and they systematically cooperate with each other and help your body to sustain and get through. Helps your body to grow, helps your body to fight, etc., etc. There are n number of functions they will cooperate with each other and perform. Now, it's a huge topic and practically not possible in 1 hour's time to touch upon everything. But yes, very, very important things will be just discussed in brief. I am saying brief because there is so much to it that we can actually talk on and on and on. So like I said, the molecules that are primarily made up of non-living elements like the carbon, the hydrogen, primarily carbon and hydrogen along with oxygen, and other elements like nitrogen, oxygen, phosphorus, sulfur, etc. So because they are present in the living organisms, they are called as the biomolecules. So among these, two of which we are going to discuss very much a little in detail are the carbohydrates and the proteins, and a little bit of the nucleic acids. Okay, so moving on further, carbohydrate. Now, if you go by the name, as the name says, carbohydrate, okay, you can actually relate this, literally to carbo means anything that will be dealing with carbon, and hydrate is to do with hydrates. Now, initially carbohydrates were thought to be, now there is a different definition to it, but initially carbohydrates were thought to be hydrates of carbon. Hydrates are nothing but water molecules. So I can write something like this. CXH2OY, that is having X number, whatever the number of carbon atoms is, and the carbon atoms will be linked to water molecules some Y number. So basically it was taught to be carbon linked to different water molecules and hence hydrates of carbon. Okay, however, this definition does not hold good to all the carbohydrates which are actually carbohydrates, and also does not hold good to some molecules which are not carbohydrates but they do fit into this formula. For example, the most common carbohydrate that we know, glucose. We know the formula of glucose is C6H12O6. Now there is another way I can write this by clubbing hydrogen and oxygen together to be written as water. So I can write this formula also as C6H2O6. Now you can expand this and you get back the previous formula, that is C6 will remain the way it is. H2 multiplied by 6 gives you 12 hydrogen atoms and oxygen multiplied by 6 gives you 6 oxygen atoms. So if you notice that this formula fits into the general formula that I have written here, that is CXH2OY. So if you correlate this, X here takes the number 6 and Y here takes the number 6. So basically glucose is a carbohydrate that fits into this generalized formula having some number of carbon atoms and some number of water molecules. Okay, so this is good as of now. However, there are some molecules like acetic acid. Now acetic acid we know is a carboxylic acid. It is not a carbohydrate, but if you simplify the formula, that is CH3COOH, into a form of this kind, okay, I can write this as C2 and I can club all the hydrogens and oxygens and write it as water multiplied by 2. So if I open this up, I get back the formula. Now this formula also relates to a formula that I have generalized here, also fits in this. Which brings me to the conclusion that even if the formula fits into this formula, it may not be a carbohydrate. Like carboxylic, this acetic acid is a carboxylic acid. It is not a carbohydrate. Okay, so it's not a carbohydrate. Further, there is another example of carbohydrate, rhamnose. Rhamnose formula is C6H12O5. Now this formula, if I want to write in this form, it is not possible because there are 12 hydrogen atoms and 5. So there is an even number and there is an odd number. So I cannot write water molecules in this way. At the most what I can write is H2O5, which will leave me with another hydrogen. So this is not a formula that fits into this. Okay, I am hoping you are understanding this, and that is why rhamnose also cannot fit into this generalized formula. So this is only to show you that even if the earlier definition of carbohydrates were all those compounds which are hydrates of carbon, it does not hold good. Reason is there are some molecules of carbohydrates which are actually carbohydrates like rhamnose, but their formula does not fit into this formula. Also, there are some molecules having a formula that fits into this generalized formula, but they are not carbohydrates like the acetic acid. So if this is not good, there has to be a correction made, correct? And the correction given is carbohydrates are now actually called as optically active. You know, the optically active comes from the chirality. Optically active, and I have put that in red because that is very important to know that they are polyhydroxy aldehydes or ketones. So they are carbohydrates are basically containing functional groups of aldehyde or it's a ketone along with hydroxyl groups, that is the OH group. Polyhydroxy indicates many OH groups along with an aldehydic group or a ketonic group, or they are compounds which give aldehyde or ketone upon hydrolysis, give such units upon hydrolysis. So, what you have to remember is basically they will be containing an aldehyde group or a ketonic group along with some OH groups, that is hydroxyl groups. Okay, so the first thing that we'll learn is classification of these carbohydrates, because having so many types of carbohydrates in different organisms, right from the cellulose in the plants, the amylose in the animal, the glucose, the fructose, they are a chunk of them. So, there have to be ways of systematically grouping them, correct? And one way that we can group them, one way of classifying them is depending on how many monomers they have. If you know what monomers are, what are monomers? They are the smallest units of any polymer. So, a big compound is made up of small units. The smallest of them is called as the monomer. So, depending on how many units of monomers are there, that is one way of classifying carbohydrates. Okay, what do you see next? So, there are three major categories of carbohydrates. One is monosaccharides. Okay, let me just mention to you that carbohydrates are also called as saccharides. Sorry about that. They are called as saccharides, and depending on the number of the units they have, they are classified as monosaccharides, oligosaccharides and polysaccharides. Now, monosaccharides, as the word says, mono is one. So, all those carbohydrates that have only one unit of the monomer, okay, that is the smallest unit is only one, is called as the monosaccharides. For example, glucose, the simplest one, glucose, fructose, ribose. Fructose is the one that is present in most of your fruits and honey. Then ribose, ribose is a carbohydrate that is a major constituent of the nucleic acids. We are going to learn that further. And galactose, which is called as the milk saccharide. Okay, so all these are examples of monosaccharides having only one unit. Then there is another category, oligosaccharides. Now, oligo means literally few. Okay, oligosaccharides are those carbohydrates that contain either 2 to 10. So, maybe 2, maybe 3, maybe 4, up to 10 units of the monomers. Okay, now what do I mean by that? For example, sucrose. Now, sucrose is made up of two types of monomer unit. One is glucose and the other one is fructose. Okay, so basically it contains, now glucose you know is a monosaccharide, correct? Fructose you also know is a monosaccharide. One unit of glucose and one unit of fructose are linked together, that becomes one unit of sucrose. And because they contain 2 units of the monosaccharides, they are called as disaccharides. Then if there are 3 units of monomers, for example, you can see raffinose, it contains glucose, 1 unit of glucose, 1 unit of fructose and 1 unit of galactose. So, 3 units, and therefore it is called as a trisaccharide. Likewise, there is styrose, which contains 4 units of monomers. One is glucose, one is fructose, and it contains 2 units of galactose. So, all of these single units like single glucose is a monosaccharide, single fructose is a monosaccharide, but glucose and fructose together makes a oligosaccharide. Okay? So, what are oligosaccharides? All those saccharides, all those carbohydrates that contain either 2 to 10 units of the monosaccharide, either 2, either 3, 4, up to 10 units. So, oligo technically means few, having few units. So, that is oligosaccharides, and then things get even more complicated about 10 units. If there are more than 10 monosaccharides that are linked together, then they are not called as oligosaccharides, then they will be called as polysaccharides. Poly means many, right. So, if you have many units, for example, starch. Starch is the major component in plants, correct. Now, starch is made up of n number of glucose units linked together. So, that is polysaccharides. So, this is one way of classifying them broadly depending on how many monomers you have. Further, There is another way of classifying carbohydrates. There are sugars called as reducing sugars and there are sugars called as non-reducing sugars. Now this you would have known a little better if we were learning disaccharides, but unfortunately that portion is deleted for evaluation for this year. But anyway, now those which can reduce, if you have heard of Tollens solution and Fehling solution, those sugars which can reduce Tollens and Fehlings are called as reducing. Those which cannot are called as non-reducing. Now this depends if whether they have a carbonyl group free or not. Okay, now I am not going into detail of that, not required for now. So just remember there are again there is this category called as reducing sugars and non-reducing sugars. Further, again monosaccharides, we said monosaccharides are single units, that means having only one unit of monomer. However, that single unit of monomer may have many carbon atoms. So depending on how many number of carbon atoms are there, they are further classified. Okay, now there is this table you have to follow. For example, in general it is to be ended as O's. Okay, so if the monosaccharide contains 3 carbon atoms, 3 is tri, so they are called as triose. If there are 4, 4 is tetra, that will be called as tetrose. Then 5 will be called as pentose and so on. I told you way back that carbohydrates contain either an aldehyde or a ketone. Depending on whether it contains aldehyde or ketone, that monosaccharide will be further so called. For example, if it contains an aldehyde and if it contains 3 carbon atoms, it will be called as aldotriose. Aldo for aldehyde, tri for 3 carbon atoms, and it is to be, the sugars are to be ended with O's. So aldotriose, and if it is a ketonic group, it will be called as ketotriose. For example, glucose. Glucose, we know the formula, C6H12O6. There are 6 carbon atoms and the functional group in glucose is an aldehyde. Fructose also has the same formula. The only difference between glucose and fructose is the functional group. Glucose contains an aldehyde whereas fructose contains a ketone. Therefore, glucose having 6 carbon atoms will be called as aldohexose. Fructose with 6 carbon atoms and a ketonic group will be called as ketohexose. So, this is one way of classifying monosaccharides depending on the number of carbon atoms and depending on the functional group, whether it is aldehyde or ketone. So, you have to remember further when we are learning glucose in detail that glucose is a aldohexose whereas fructose is a ketohexose. Hexose because both of them have 6 carbon atoms. Okay. So, both these glucose and fructose we are going to learn a little in detail. More importantly, their chemical structure. Okay. So, moving on, glucose is one of the most important carbohydrate, you know. Anybody just needs energy, quickly he is given glucose to boost the energy. It is found in fruits, honey, any sweet vegetables, then grapes has large amount. Now, how can you prepare glucose commercially? If I go back, I told you here, see this, sucrose. Sucrose is made up of glucose and fructose. So, if you want to prepare glucose, you can simply take sucrose and break it down, hydrolyze it. Hydrolyze is breaking down of it, it will give you glucose and fructose. Also starch. Starch is also made up of glucose, correct? So, if you are able to hydrolyze starch, it will break down into its constituent which is nothing but glucose. So, that is how commercially glucose is prepared. Okay. So, there is one way of preparing glucose from sucrose. Why? Because sucrose is made up of 1 unit of glucose and 1 unit of fructose. So, you simply hydrolyze this with an acid like HCl or H2SO4, it will break down into its constituents, that is glucose and fructose. So, that is one way. Another one that we discussed just now, that it is present in starch which is a polysaccharide. So, you can simply on a commercial basis you can break down or hydrolyze this starch, it will break down into its constituent, that is glucose. Okay, so sometimes our what do you say, question papers, you will find this question, and it is also important on a commercial scale how it is prepared. Okay, now what next is we have to learn the structure of glucose. Now what we are learning in this part is basically how to deduce the structure of glucose. Now consider that you know nothing about glucose except that you know its formula. The formula is C6H12O6 and you know nothing else. You do not know how these carbon atoms are bonded to each other. You do not know how the hydrogen and the oxygen is bonded to carbon or within themselves. You know nothing. So then how do you deduce the structure? This is what is done to any unknown substance that you analyze. What you do is you perform different tests, okay, and you treat the results of this tests as evidences and you put it all together and use all your knowledge, and that is how you deduce the structure, okay, and that is exactly what we are going to do with glucose. So there are some reactions of glucose that you have to be knowing and the inferences from those reactions, and then you club all that and you deduce the structure of glucose. Okay. So what is the first thing? First thing you know is its formula, and you also know, because I am telling you now, that it is called as dextrose. Okay. Now why dextrose? If you know that dextrorotatory and levorotatory. Okay. Glucose is a compound that is dextrorotatory. How do you find this dextro or levorotatory? It has nothing to do with the structure. Dextrorotatory and levorotatory, I mean you cannot look at the structure and find out, that is what I mean. What you have to be doing is to find out whether it is dextro or levorotatory, you have to put it in the instrument. If it rotates the light of plane polarized light to the right, it is dextrorotatory. If it rotates the light to the left, it is levorotatory. So when you take glucose, you take the substance and you put it in the polarimeter, it will rotate the light to the right. That is how you know that it is dextrorotatory. So that is another thing you have to know. Now because it is dextrorotatory, it is called as dextrose. Further, we know that it is a monomer in many carbohydrates like starch and cellulose. Starch, I just now told you that it is entirely made up of n number of glucose units. Now what are the reactions? These reactions are very important. Okay. The first reaction is when you treat glucose with hydrogen iodide, what you get is a N-hexane. Now what is an N-hexane? Hexane is having 6 number of carbon atoms all linked in a straight chain. So this shows that first of all the 6 carbon atoms that are present must be all linked in a straight chain. There is no branching. This is what you come to know from this evidence, because on treating with Hi, that is hydrogen iodide, it gives N-hexane. So from here this is what I infer. Okay. First thing I get to know is the skeleton of the glucose. The structure skeleton is that the carbon atoms are all arranged in a straight line. Then further there are some reactions like if you treat glucose with hydroxylamine, it will form an oxime. Now this is a typical reaction of a carbonyl group, okay, an aldehyde group in fact. If you treat any aldehyde group with hydroxylamine, it will give you an oxime. Similarly, there is another reaction which is also very typical of carbonyl group, that is when you treat it with HCN, it adds on hydrogen cyanide to give you cyanohydrine. Okay, so you have to pay attention to this. I have not written the structure, I have written only the formula, but what you get is a C double bond O, that is a carbonyl group will break and you get an added product H, it is HCN, right, CN and hydrogen. This oxygen already belongs to the compound. Now these two reactions are typical reactions of a carbonyl group. So if glucose is showing both these reactions, it straight away indicates that there must be one carbonyl group. Okay, so this is what. So, if you are asked to give a reaction, for example, to prove the presence of a carbonyl group, you can give one of these, okay, or both of these. Okay, so what do we know as of now? From the first reaction, that is treatment with HI, we know that the 6 carbon atoms are all linked in a straight chain, and the second thing we know is that there is a carbonyl group. Okay. The next thing is you get to know that the carbonyl group is not a ketonic group, but it is an aldehyde group. Why? Because when it is treated, when glucose is treated or when it is oxidized using a mild oxidizing agent like bromine water, the aldehyde group gets oxidized to carboxylic group, okay, or the carbonyl group gets oxidized easily to carboxylic group, which indicates the presence of an aldehyde group, because this is, you are using a mild oxidizing agent. This is an the reaction which is shown by aldehyde group. Okay, any aldehyde group with mild oxidizing agent will quickly get oxidized to carboxylic group. So, this what do you say, this is an evidence for the presence of an aldehyde group. So, what do we know as of now? First, we know that the carbon atoms are all linked in a straight chain. Second, we know that there is a carbonyl group from the previous 2 reactions. A carboxylic group, that is aldehyde group, gets oxidized to carboxylic group, and hence this is what we arrive at, that there are carbon atoms and there is a carbonyl group. The carbonyl group is actually an aldehyde group and not a ketonic group. Now, the next reaction is acetylation of glucose with acetic anhydride. Now, this is a typical example of an alcoholic group. A OH group gives you an acetate. Glucose pentaacetate is what you get on treatment of glucose with acetic anhydride. So, this is an evidence that there are, since it is giving pentaacetate, there are 5 OH groups in the glucose molecule. Now, we know that a what do you say, OH group cannot be, there cannot be 2 or more OH groups present on one carbon atom, because then it makes the compound unstable, but glucose is very much stable. So, the 5 OH groups as indicated by this reaction must be present on 5 different carbon atoms. Okay. So, as of now, that is what we infer. 1, there are 6 carbon atoms in a straight chain. Second, there is a carbonyl group. The carbonyl group is actually an aldehyde group, because on reaction with bromine water, which is a mild oxidizing agent, the aldehyde group gets oxidized to carboxylic group. Also, with acetic anhydride, it gives pentaacetate. Penta indicates that there must be 5 OH groups, and these 5 OH groups must be present on 5 different carbon atoms, because glucose is a stable molecule. Further, on strong oxidation, that is with nitric acid, because nitric acid is a strong oxidizing agent, we get a dicarboxylic acid which is called as the saccharic acid, and that is the formula of the saccharic acid, with 2 COOH groups at 2 terminals, which indicates that there must be a primary alcoholic group. There has to be one primary alcoholic group. So, this indicates that the 2 COOH group is a result of oxidation of both the aldehyde group as well as the primary alcoholic group. The aldehyde group gets oxidized to COOH, and also the primary alcoholic group also gets oxidized to COOH group. Now, with all these evidences, that is the formula, the chemical reactions and everything, you can put together, and Fischer gave a way of projecting this, that is a way of writing this called as the Fischer projection, and this is what he proposed. Very, very important. The open structure of glucose was precisely proposed to be like this, with the correct orientation of the OH group. Now, what do I mean by that? So, first thing, there are 6 carbon atoms all linked in a straight chain. Second, there is a carbonyl group which is the aldehyde group. So, since it is an aldehyde group, it has to be in the terminal. So, that is the group, that is C double bond OH, which is the aldehyde group. Then there is one primary OH group which will have to be put in the other end because it is a primary, and you are left with 4 OH groups, and precisely these OH groups have to be oriented like this. What I mean by that? The one that is on the second carbon has to be on the right, left, right, right, and that is precisely the structure, open chain structure of glucose, which is arrived using all those evidences, that is all those reactions that we discussed all this time, and it is to be named as D plus glucose. Now let me explain to you what this is. Plus comes from its optical activity. You have to remember this, that the plus is because it is dextrorotatory. Okay? It is either written as small d and small l for dextrorotatory, levorotatory, or it is written as plus and minus. So we have learned earlier that glucose is a dextrose because it is dextrorotatory, and therefore this plus. Now what is this D? Now the capital D is not to be confused with the optical activity. This capital D is coming from its configuration, that is from the structure. Okay? How? Is you have to look at the OH which is on the 5th carbon. Okay? If this OH is on the right hand side, so here it is on the right hand side, so the D is not to be confused with the small d and l which is for optical activity. Here the D is for configuration and the plus is for indicating that it is dextrorotatory. So let me talk about configuration again. So I was saying you have to look at this OH which is on the 5th carbon. Why the 5th carbon? The carbon which is adjacent to the terminal carbon. So the terminal carbon here is carbon number 6, adjacent to that is carbon number 5. So if the OH is on the right hand side of the carbon, then it is to be called as capital D, to be written as capital D. Now this is compared, the D, capital D and L is compared to glyceraldehyde, which is taken as a standard. Okay, now I am not taking that in detail here, just remember that you have to look at the carbon which is adjacent to the terminal carbon. So that is how you have it called as capital D plus glucose. So yes, it is correctly named as D plus glucose. D is because the OH is on the right hand side. Which OH? The OH which is adjacent to the terminal carbon, and the plus is because it is dextrorotatory. D or L comes from the structure. You have to look at the structure and predict whether it is D and L, D or L, and plus minus cannot be predicted from the structure. Plus minus is to be predicted by using the instrument. Further, the letter in D and L is therefore because of the configuration, it has nothing to do with the optical activity. Now it does not end here, this is just the open structure. Now, so having said that, it does not give the 2,4-DNP test, it does not give the shift test, it does not form hydrogen sulfide. It indicates that the CHO group, even though it is present, it must be not free, suggesting therefore that it must be therefore bonded with something, and the structure may not be free and it must be a cyclic structure. Therefore, it was suggested that the following are the possibilities how it can form the cyclic structure. Why? So, you know that the carbonyl group, because there is an electronegativity difference, oxygen is more electronegative than carbon, and therefore, I can say that because of the electronegativity difference here, carbon will slightly get a positive charge, carbon will slightly get a positive charge, a partial positive charge, and oxygen will get a partial negative charge. That comes from the electronegativity difference. Now, because this carbon is slightly electropositive, it has an affinity. You see there are so many OH groups here and the oxygens are electron rich. There are so many electrons available here, and therefore this carbon which is less in electrons and less a negative charge feels greedy for these electrons. So it could attract these electrons and form a new bond. Now if it attracts this one, that is from carbon number 2, if it attracts the one that is on carbon number 2, it will form a very small cycle. That's a very tiny cycle and there will be lot of strain. Likewise, even this will be small. So the preferred cycle or the preferred bond it forms is with the oxygen that is on carbon number 5. There is actually a tendency for any of these, but actually it forms with carbon number 5, and there are various reasons actually different scientists have put up to explain why 5 and why not the others. Okay, because then there is strain and there is stress and so much that comes into picture. So it is the oxygen that is on carbon number 5 that will form a new bond with the carbonyl carbon, that is carbon number 1. How? Here, the oxygen has lone pair of electrons that will be attracted by the carbon. Now this carbon already has its 4 bonds. So if there is a new bond that is being formed between carbon, this oxygen, and of course the hydrogen will get lost from here, the oxygen gets deprotonated, that is hydrogen is lost. Okay. So there is a new bond between the electrons of oxygen that is forming a bond with carbon. And since this carbon already has a 4 bonds, 1, 2, 3, 4, and there is another one that's being formed now, one of the bond will have to move. So it is this that moves with a pair of electrons onto oxygen. So therefore you see that there is a new bond between carbon, the oxygen and this carbon, that's carbon number 1. And then what happens to the oxygen? Oxygen becomes O minus because it gets lone pair of electrons from this bond and it picks up the proton. So you have now generated a new carbon oxygen carbon bond, which is this, which is shown in dotted, carbon oxygen carbon, that's the new bond forming a cycle. Also the oxygen which was already there now will pick up this H with the lone pair on electrons will pick up this H and form and generate a new OH. This is very important, that the new OH that is formed, you will have to place this now, where either on the right hand side or on the left hand side, and that is also very important because that is how then you have another 2 isomers of glucose called as anomers. If you put the OH on the right hand side, it is called as the alpha anomer. Alpha ones are the ones in which the OH on the carbon, which was earlier the carbonyl carbon, which was a functional group, and now it is called as the anomeric carbon. If the OH is on the right, it will be called as alpha glucose, and if the OH is on the left, it will be called as beta glucose. Okay, so let me just put this up again. What is happening here? Oxygen having lone pair of electrons here gets attracted by this carbon. Why? Because this carbon is electropositive. Okay, it has partial positive charge, and therefore there will be a new bond between carbon, oxygen, this carbon. Okay, and this hydrogen will be lost and it will be picked up by the oxygen, forming a OH. So that OH that is formed has to be put either on the right or to the left, the new OH. So it is this OH. So the carbon number 1, which was earlier before cyclization, the carbon was a carbonyl carbon. Now after cyclization, the carbon has another new OH onto it. Now that carbon is now called as an anomeric carbon, and if the OH is on the left hand side of that anomeric carbon, it is called as the beta anomer, and if the OH is on the right hand side of the anomeric carbon, it is called as the alpha anomer. So this alpha and beta are 2 anomers of glucose. Also you have to pay attention that now that it has cyclized, it is forming a 1, 2, 3, 4, 5 carbon atoms and 1 oxygen, total 6 membered ring. Okay, so basically the cyclic structure of glucose is a 6-membered ring, out of which 1 is an oxygen and 5 carbon atoms. So this is all coming in the ring. So what we have to do next is write the ring structure, okay, which is called as the Haworth projection. Before that, the ring so formed is called as a hemiacetal ring, okay, because it's an aldehyde and it's forming an hemiacetal. So you have hemiacetal and you have hemiketal. So what next is writing this structure in the ring form. So we said that glucose exists in 2 different forms, alpha and beta, which is called as the anomers. Alpha I told you because of the OH on the right, beta because the OH is on the left. Now from here we have to write its something called as Haworth projection. This way of writing is it is Fischer projection, and Haworth projection is writing the cyclic structure of the open structure. Cyclic structure, now here you know how many things are coming in the cycle. So this carbon, that's carbon number 1, carbon number 2, 3, 4, 5. This is all coming in cycle, and also the oxygen is coming in cycle. So it's a 6-membered ring. So first thing you do is from here to here, how to draw? Draw a 6-membered ring. What's a 6-membered ring? A hexagon. Okay, so you typically have to draw a hexagon with one of the corners occupied by oxygen. This is what. Okay, the next thing is you put dashes like this on every corner to indicate other groups present on that carbon. Okay, so then next you number them. So I have started from here. This is oxygen. Oxygen is bonded to this. What is this? Carbon number 1. So next to oxygen, you can start this way also, or you can start this way, clockwise or anti-clockwise, the way you want. So oxygen is bonded to carbon number 1. So next to oxygen, that corner, I am going to call it carbon number 1. So I number these carbons now. So that's my carbon number 1. Next is carbon 2, carbon 3, carbon 4, carbon 5. What next? What is there on carbon number 1? On carbon 1 there is a hydrogen and there is a OH, which you have to put on this carbon, hydrogen and OH. How to go about this? Whatever is on the right hand side, okay, remember this, whatever is on the right hand side is to be put down. Okay, now what's on the right hand side of carbon number 1? OH. So I put my OH down. On carbon number 2, what is on the right? OH. So I put my OH down. On carbon 3, what is on right? Hydrogen. So I put my hydrogen down, and so on. So on carbon 4, there is OH on the right, I put it down. On carbon 5, now here you have to be careful. On carbon 5, there is no right and left, you see. There is CH2OH. Now this is a big group. For convenience, the big group is not put inside the ring. It is to be put up. So I put CH2OH up and I put H down. Okay, and then rest of the things you put. So what is there on carbon 1 other than oxygen? Hydrogen. So yes, hydrogen, hydrogen, on this is OH and then there is H. So that is the way of writing a Haworth projection. From open structure, how you write, meaning from Fischer projection, this is cyclic of course. From Fischer, how do you write Haworth? That is the way. Okay, so whatever is on the right has to be put down. Remember that, and just how many membered ring is there you see, and draw a skeleton. Then put the dashes and fill up. That's all. Okay, so that's the structure. There are 2 anomers we said, alpha and beta. Alpha because this OH is on the right, and here beta because this OH is on the left. What we just discussed all this time. Rest everything remains the same. And this from here, that's a Fischer projection. You have to draw the Haworth projection. So that's the alpha anomer and that's the beta. Alpha is what we just drew and beta will be just the opposite only at carbon number 1. Rest everything remains the same. Okay, so this is what we discussed. The hemiacetal cyclic rings of glucose differ only at the configuration at carbon number 1. Rest all configurations are same. So you see the beauty of chemistry with only one, what do you say, not even the element changing, the elements are same, just that the spatial configuration is changing. Only with right and left the whole molecule changes. Okay, so you have whole molecule different alpha and different beta. So because of this similarity with a 6-membered ring wherein there is 1 oxygen and 5 carbon atoms is similar to the structure of cyclic structure of glucose that we just learned. Glucose is correctly named as alpha D plus glucopyranose. Okay? So you have to know each term why it is so called. Glucopyranose because it's glucose, pyranose because it has similarity with the pyran ring, plus is because it is dextrorotatory and not from the structure. D is because the OH on the adjacent carbon to the terminal is on the right hand side, and alpha is because the OH on the anomeric carbon is on the right hand side. So that's the complete name of glucose, and this is the complete cyclic structure of glucose. With each term you have to know why it is so called. That's about glucose. Now similarly there is another very important monosaccharide, just like glucose, having the same formula, having the same number of carbon atoms, hydrogen, oxygen atoms, which is fructose, okay, which is found in most of our fruits and it is present in honey, and it is having the same formula as fructose, as glucose. However, just that it is ketohexose. Okay, I told you earlier also. Glucose is a aldohexose, whereas fructose is a ketohexose. Keto because there is a ketonic group, hexose because there are 6 carbon atoms, and it is obtained along with glucose by hydrolysis of sucrose. The difference between glucose and fructose is, one is its functional group, and number 2 its rotation. Okay, fructose is levorotatory, whereas glucose we saw it's called as dextrose. Why? Because it is dextrorotatory. That is why we put plus in that bracket, because it is dextrorotatory, glucose. Fructose on the other hand is levorotatory. Now just a happy news for you that you don't have to know the evidences to arrive at the structure. Like for glucose you have to know this equations, no? You have to know what happens with HI, what happens with the hydrazine, all those. You don't have to, sorry not hydrazine, with the hydrogen cyanide. You don't have to know those for fructose, straight away jumping on to the structure. That's the open structure straight ready for you of fructose, which is called as the Fischer projection. 6 carbon atoms all linked in a straight chain. There is a ketonic group. You know the ketonic group cannot be terminal carbon. So it is carbon number 2, that is the ketonic group, and also you have to know the arrangement of OH. This is on the left, this is on the right, this is on the right. Similarly, just like glucose, fructose is also known to exist in the cyclic form for similar reason. What is the reason? The carbonyl carbon, which is having a partial positive charge. Why does it have a partial positive charge? Because of the electronegativity difference between carbon and oxygen. We discussed this for glucose. Because carbon has a partial positive charge, it has affinity, it is greedy for these electrons. There are so many electrons here that it can attract. In fact, it does not attract these, but same carbon number 5. The oxygen on the carbon number 5 forms a new bond with carbon. That is carbon number 2 here. So, how many membered ring will you get in this case? You will get 1, 2, 3, 4 carbons and a new bond between carbon, oxygen and carbon. I am showing it to you in the next slide here. Same way, just like we did for glucose, same thing for fructose. So, here there is a new bond between, let me show you. In this case, it is this oxygen that will be having a lone pair, which will be attracted by which carbon? This carbonyl carbon. Obviously, this bond cannot then sustain with its electron, it will go to oxygen and this hydrogen will be lost. Oxygen gets deprotonated and this hydrogen is then picked up by this oxygen. Okay, so there is a new bond between carbon, oxygen, carbon, and there is a new OH generated from where? From this oxygen picking up the hydrogen, similar to what we learnt in glucose. So, I have straight away shown you this structure. So, the OH, the new OH that is formed can either be on the right or it can be on the left. Okay, so this becomes the anomeric carbon now. This carbon, which was earlier the carbonyl carbon before cyclization, is now called as the anomeric carbon. So, if the new generated OH is on the right hand side, then it will be called as alpha. And if the new generated OH is on the left hand side, it will be called as beta. And how many membered ring now does it form? 1, 2, 3, 4 carbons and plus 1 oxygen. So, total 5 membered ring. So, from here how to draw the Haworth projection also we have learned for glucose. So, what you have to do is draw 5 membered ring. What's a 5 membered ring? A pentagon. So, draw a pentagon 1, 2, 3, 4, 5 and in one corner you put oxygen. Then put your dashes that was shown to you earlier, put all your dashes and then how do you go about from writing here from this to this? Whatever is on the right hand side is to be put down, correct? So, on carbon number, now this is your oxygen, this is carbon number 1, this carbon. So, on carbon number 1, what is on the right? OH. So, I put that OH down. On carbon number 2, what is on the right? Hydrogen. So, I put my hydrogen down. On carbon number 3, what is on the right? OH. OH goes down. On carbon number 4, you have 2 groups, that is CH2OH and H. So, CH2OH by convention for convenience goes up, it is to be put up. Okay, and same way you go about writing the structure for the beta ionomer. It is the same thing. If you've understood this well, glucose have to go about, you will be able to write fructose very easily. All that you have to remember for fructose is the carbonyl carbon is on carbon number 2, that is the carbonyl carbon, and the ring is formed between same carbon 5 and the carbonyl carbon. Okay? And once you form a ring, how is the ring formed? Between carbon, oxygen and carbon. What happens to the oxygen that was already there? It forms OH. H comes from where? This hydrogen. So, that new OH has to be put either on the right or to the left. If you put it on the right, it becomes alpha. If you put it on the left, it becomes beta. If it is alpha, it is to be called as alpha D fructofuranose. Why D? If you are thinking because it is anything to do with dextro or levo, then sorry, you have mistaken. This D is why? Because here I am showing you the open structure. This OH, which is adjacent to the terminal carbon, this OH is on the right and that is why it is D. That comes from the configuration. Okay, so hence it is alpha D fructofuranose. Why furanose? Okay, I think I didn't mention to you this. Furanose because it is to be compared, just like glucose is compared to the pyran ring. Going back, glucose is compared to a pyran ring. What's a pyran ring? A 6-membered ring with 1 oxygen, 5 carbons. Likewise, a 5-membered ring is having 4 carbons, that is 1, 2, 3, 4, 4 carbons and 1 oxygen. So, that is a furan ring. So, because it has an analogy to the furan ring, it is called as furanose, that is fructofuranose. So, because of the similarity with furan, it is called as furanose and the complete name is therefore either alpha D fructofuranose or alpha D, beta D fructofuranose. So, that is about fructose and in fact that is all about carbohydrates. For now we will stop here and the next topic, that is proteins, we shall continue in the next lecture. Thank you very much.
Prudent Scholars, powered by Lupin Pharmaceuticals.